First of all, I'd like to thank the organizers, Hunying, Thomas, Angela, and Beyond, and also the secretaries here that I know that to organize such a conference in this unusual situations, it needs a lot of work, and so I thank you very much. I feel honored to be here, and also I'm very pleased to be back to Singapore. So the subject of my talk, series of lectures, is new directions of the study between geometry and representation theory. I plan to explain some basic notions, basic results, and some key ideas, but not in details, but try to explain a lot of examples and then explain its ideas. So I plan to organize 3 lectures in the following. The first today, I plan to talk about some general topology and transformation groups. So with focus on proper actions. So the definition of proper actions is very simple, but the conditions is quite delicate. So we shall see that this definition is not a local one, but a global properties. And sometimes, even though there's no singularities, but sometimes properness fail. So we shall see such delicate examples, and then give necessary sufficient conditions for proper actions for reductive groups. And since the title of this talk lectures conference is revisiting the works of Hausdorff and Lebel, in the second and third lectures, I discuss the following. The first one is that, so the idea is that today I explain some qualitative results, but then propose 2 directions of quantifications. One is to strengthen properness conditions. And this idea will be explained tomorrow, and then discuss about base local rigidity, which is classically formulated for the Riemannian setting. But we are curious about when it is beyond the Riemannian setting. And then still in some cases, local rigidity holds, but in some other cases, we have a more deformation space, like a higher Teichmüller theory. And to study such, we use as a tool quantifying properness actions, stronger proper action. And then the third one is purely representation theory, that if the action is not proper, then we may also propose how to quantify to which extent the actions is far from being proper. And this idea, based on the dynamical approach, gives some results on representation theory. And so I plan to talk about tempered subgroups in the sense of the Margulis, and then tempered homogeneous space. The naming is similar, but it's a little bit different, and I shall clarify this. Okay, so this is a rough plan of the series of lectures. Now, let us start for today's topic. So we recall some classical Riemannian geometry, and then the local to global study has been a major trend of 20th century geometry, and still now it's a very active research area. And there have been remarkable developments since 20th century in Riemannian geometry. Typical example is that think of the spheres, and the sphere is at every point it is positive curved space, and also it is compact. And positive curved is a local property, and compactness is global properties. And such result holds if we perturb the structures. For example, Bonnet-Meyer theorem says that any complete manifold, Riemannian manifold, is compact if its rich curvature has a positive pinching, namely, it is strictly larger than some positive number. And the diameter is expressed by this upper bound of the diameter is expressed by this number. So this is a typical example from local to global studies. So this is curvature is a local property, and then compactness global property. Then, but most of the proof used heavily that the metric tensor is positive definite, or the ball is compact. So we may ask ourselves, how about the local to global study in pseudo-Riemannian geometry, such as the Lorentzian geometries? So we recall some basic notions that suppose X is a manifold, and at each point, if we are given a non-degenerate bilinear form, Gx, that depends smoothly on X, then such a manifold is called pseudo-Riemannian manifold. By Sylvester's law, that the signatures is locally constant. And if it is positive definite, this is the definition of the Riemannian manifold. And if the signatures, there's one minus, and then the other is positive, and then this is called the Lorentzian manifold. And the pseudo-Riemannian manifold treats the general signature P and Q. Typical examples with large isometry is given by pair of real reductive Lie groups like GLNR, or indefinite orthogonal group OPQ, or symplectic group SPNL. And then by using the Killing form or extensions to central parts, then the homogeneous space Z mod H carries pseudo-Riemannian structures on which the group Z acts isometrically. So the isometric group is large one. So this is a typical constructions of pseudo-Riemannian manifold with large isometric group. Okay. Then let us consider an analogous result for the Bonnet-Meyer theorem. So we consider positive curvature space, but indefinite metric like Lorentzian metric. So then, in contrast to the Riemannian case, usually global structures of pseudo-Riemannian manifold is very hard and not much has been known. But there's a very striking result due to Calabi-Markus, saying that any de Sitter manifold is non-compact. So cannot be compact. So what is a de Sitter manifold? So de Sitter manifold is by definition a Lorentzian manifold such that its sectional curvature is constant to be positive. So this is an analog of the spheres. In the sphere, sectional curvature is constant to be positive. And then it is a compact manifold. But in the Lorentzian manifold, it's opposite situations that everywhere it is positively curved, but then the manifold cannot be compact. And the model space of the Sitter manifold is given in the Minkowski space as a hypersurface. Namely, we consider n plus one dimensional space equipped with this flat Lorentzian metric. And then restrict to the higher dimensional one seat of hyperboloid. Then induced metric is Lorentzian and with constant sectional curvatures. So this is a model space. So locally isomorphic to this one. But we cannot make a compact quotient of this manifold by isometry. So to understand this, we recall some basic notions from general topology. So suppose a locally compact group L acts on locally compact Hausdorff space. Then, for each subset S in the geometry, we define a subset LS in the group as follows. So fix S in the geometry and then translate. Then these translations may intersect with original S or maybe disjoint. And we collect all the elements of the group elements that still has an intersection. So this is the definition of LS. And in general, that the actions of non-compact groups on geometry may behave very wildly. And among all such actions of non-compact groups, we focus on nice behaved actions. This is proper action. So namely, so in this example, that if S is a singleton, then this Lx, just we may write Lx, is a stabilizer. So this is a subgroup. But in general, LS is just a subset. And reasonable or nice actions of non-compact group would be that LS is reasonably small whenever S is reasonably small. And to be rigorous, we may formulate as follows. If this set LS of the group is compact whenever S is a compact set in the geometry, we call such an action is proper action. Similarly, this LS is finite for any compact set. This action is called proper discontinuous. And lastly, for each singleton, this Lx is also identity singleton. Then this actions is called free or fixed point free actions. So these are actions which behave nicely like actions of compact group. And if X is a manifold, and if the actions is properly discontinuous and free, then the quotient space X mod gamma, namely the orbit space of these actions, becomes Hausdorff in the quotient topology. So we have a natural quotient map. And on this Hausdorff topology, this quotient carries a natural smooth manifold structure such that the quotient map becomes a covering, smooth covering. Conversely, if we are given a manifold and consider it, for example, universal covering, then we have a covering transformation group. And covering transformation group is proper discontinuous and free and recovers the original manifold. In relation to the group theory, typical example is compact Riemann surface, where the genus is 1 to G, so this G is genus. And suppose genus G is greater than or equal to 2, then by the uniformization theorem by Klein, Poincaré, and Kebe, that its universal covering is bihomomorphic to the upper half plane, so namely SL2R mod SO2. And the covering group, sometimes referred to as the surface group, is placed this rho gamma, acting proper discontinuously and freely, and recovers this compact Riemann surface by the quotient of the upper half plane by surface group. Okay, so this is what we shall look at in a more general setting. Okay, and at this moment, I like to emphasize the difference between the Riemannian and the pseudo-Riemannian geometry with respect to these transformation groups. So first, start with the classical case, namely Riemannian geometries. Then suppose that XG is a complete Riemannian manifold. And let G be the group of isometries. Then the G becomes automatically a finite dimensions D group. And let gamma be a subgroup of Z. Then in the classical Riemannian setting, the following two conditions are equivalent. The first one is that the gamma is a discrete subgroup of the isometry group Z. So this is the property of the group gamma itself inside D group. The second condition is the property of the actions. Namely, the group gamma acts properly on X as isometry. And in the Riemannian setting, these two notions are equivalent. An easy direction is that if the group acts properly discontinuously on the geometry, then the group itself is a discrete subgroup. This is very easy to prove. The opposite directions, if gamma is the discrete subgroup of isometries, then the action is properly discontinuous. This is more involved. But in the Riemannian setting, by using a similar argument of the Ascoli-Alcaraz theorem, that some uniformly continuities, and then we take a sequence of isometric transformations to converge again isometric transformations. And the proof uses that the ball is compact in the Riemannian geometry. So this is one of the key property in the proof. So the proof depends heavily on the positivity of the Riemannian tensor. Then we may ask that we can consider similar situations for pseudo-Riemannian geometry, and we may consider the group of isometries for pseudo-Riemannian manifolds. Still, the isometry group is always a Lie group. And then we may ask if these conditions are equivalent or not. So this is a previous slide. And then it turns out that if the metric tensor is not positive definite, then these two notions are not equivalent. Properly, if the actions is properly discontinuous, then automatically the group itself is discrete. This is an easy direction and still true. But opposite directions is not true. In fact, let us reinterpret the Calabi-Markus phenomenon. That we consider the modular space on which, so this modular space may be identified with the homogeneous space of the Lorentz group ON1 modulo O n-1, 1. And on which the group, Lorentz group, acts isometrically. So we consider discrete subgroup of Z. So this means that each element of gamma acts as an isometry. And also gamma itself is a discrete subgroup. However, such gamma cannot act properly discontinuously as far as gamma is infinite groups. In other words, if gamma acts properly discontinuously on the model H, then gamma must be a finite group. So in particular, if we take a quotient by finite group on this space, and this space is generalized hyperboloid, which is non-compact, and so quotient cannot be compact. So this is a key for the Calabi-Markus phenomenon. Okay, so this example shows that this property, discreteness in the isometries and proper discontinuous actions is very different notion. Okay, so to analyze this, we write such formulas. So namely, in the topological space, finite set is nothing but compact and simultaneously discrete. Similarly, we recall the definitions of proper discontinuous actions, saying that for each compact set S, the set LS is finite. So this is the definition. And if we use these formulas, then this amounts to that. This is proper actions, and the group itself is discrete. And if we write this way, then two property is the property of the actions. And this property is not a property of the actions, but this property is just a property of the group itself. And so we want to look at the difference between discrete subgroup and proper discontinuous actions. So what we need to focus on is to understand the proper action. So we shall give criterions for proper actions very soon. The key is this formula. Also, I'd like to introduce terminologies. Sometimes in the classical Riemannian setting, in particular Riemannian symmetric space, this terminology is mixed. But if we want to consider more general setting where the geometry is not necessarily Riemannians, we need to use the terminology rigorously. And so we use the terminology discontinuous group is that gamma is not only discrete subgroup of Z, but also the action of gamma on X is proper, namely proper discontinuous actions. In such a case, we use the terminology gamma is a discontinuous group for the geometry X. So this is sometimes I shall use this terminology today and also tomorrow's lecture. Okay. So the definitions of proper actions, I just rewrite equivalent way, but the proof is very easy. But, for this, we also recall the notions, proper maps between locally compact Hausdorff spaces. So the definitions of proper maps depends on the literatures. For example, different from this one, for example, the definition of the Bourbak's book is different from this. But if we assume X and Y are locally compact Hausdorff spaces, then the definitions of proper maps are the same in different literatures. And we shall usually consider only manifold, so I just use this definition. Namely, a continuous map is called proper if for any compact subset S in the target space, the full inverse is compact. So this is the definitions. Then the actions of the proper action, definition of the proper actions that we defined is that we defined LS is compact for any compact subset S in X. But we may write in the following way, that we consider the natural map from the actions. The first one is the projections, and the second one is the action map. Then we have a map from the direct product from L times X to the direct product of geometry X times X. And this map is a proper map. These definitions, or equivalently, I write LS to T, where this is a collection of group elements such that GS has a non-trivial intersection with T. And this set is compact for any compact set S and T. And of course, if S equals T, then this is a previous definitions of LS. And this equivalence is easy to be verified. But I put this definitions because one reason that I want to recall the definition of the proper maps. And also another reason is that in the third lectures, we consider much weaker definitions that measurably proper action. So these conditions is compact is equivalent to say that the volume of this subset with respect to the Hall measure is finite for any S and T. So this is also easy to check. But then we replace S by one point X. And then also these conditions, finite volume for almost every X for any compact set T. So this is measurable proper actions. So it's a much weaker condition than this. But on the other hand, if we use measure theory, then also we may apply functional analysis to the study of the topology. And also we may use representation theory, like asymptotic behavior of matrix coefficients and so on. So this is one of the tool to connect such notions and unitary representation theory. So this is the reason why I introduced such quite obvious equivalence relations for proper actions. And also proper action itself is connected with unitary representations. For example, we may think of the branching problem of unitary representations. So suppose G is a Lie group, and we consider unitary representation pi on a Hilbert space. So this is a group of unitary operators. So this is a unitary representation. And let H be a subgroup of Z. Then we may think of these representations as a representation of the subgroup by the restrictions. And the branching problem asks how the restrictions behave, like how it decomposes. So this decomposition formula is sometimes called the branching law. But also not only decompositions, but also we may consider more general questions about the behavior of this restriction. Okay, and the orbit philosophy proposed by Kirov and then later developed by Constant, Duflo, and others tells that the set of irreducible unitary representations called unitary dual will be parameterized the set of coadjuvant orbits. This is true for simply connected nilpotent Lie groups, and for semi-simple Lie groups or reductive groups, there's no such correspondence, but still the set of coadjuvant orbits is supposed to give good approximations of the unitary dual. And also we expect that such correspondence could be some functorial properties. Again, this is true for the nilpotent Lie groups, and for semi-simple Lie groups, we still have some expectations for some generic parts of this correspondence. So concerning the branching problem, we are thinking of the subgroups. They correspondingly, we may think of the projections of the dual of the Lie algebra and then restrict to H. So this is the projection. And then, for example, we may ask when the restrictions is admissible in the sense that there's no continuous spectrum and each discrete spectrum appears with finite multiplicity. This would correspond to that the composition of two map is a proper map. And I don't, in the 3 series of lectures, I don't discuss about this, but in the fourth lecture independent of this series of lectures, I may talk a little bit about this admissible restrictions. And in some cases, this conditions is characterized that for reductive groups also this compositions is a proper map. In some cases proved by Nasrin and Pardon and myself, but only for some certain settings, because this is still approximate property. Okay, so this is another relations of this geometry and representation theory. But this series of lectures, I focus on proper actions, not the proper map itself. And so, as I mentioned that this properties is responsible for proper discontinuous actions, the difference between discrete subgroups and proper discontinuous actions. So if we understand better, we would have a better understanding of proper discontinuous actions. And this discontinuous group will be responsible for the study from local to global. For example, if we highlight homogeneous structures, so like constant curvature space, so this is an locally homogeneous structures. So this is a local properties like constant curvatures. Curvatures defined infinitesimally. Then fundamental group is responsible for the global geometry, and the fundamental group on the universal covering acts properly discontinuously. So discontinuous group will be responsible for the global geometry. So this means that for the study from local to global for locally homogeneous structures, if the local structure is given by homogeneous structure, locally homogeneous structure, then the global properties will be understood better if we understand proper actions better. So this is a geometric view. And analytic view of these actions relations to decreometric quotients or tempered homogeneous space will be discussed in the other lectures. Okay. So we go back to so this is second and third, but we will go back to this part. Now maybe I too slow now. Okay. So so let us discuss about the properties of proper actions. So suppose L is a locally compact group acting continuously locally compact Hausdorff space. And if the action is proper, then we have some obvious results. One is that the quotient space is Hausdorff in the quotient topology. And also, every orbit is closed manifold, closed subset in X. And also, all the isotropy subgroup is compact. The first condition implies second. This is obvious because Hausdorff implies T1. And also, the second and third conditions are easily verified. So this is a local property in the quotient space. Namely, one point is closed in the quotient space. And the third one is also easily verified. But the Hausdorffness is not a local property, but a global property. So the first conditions is usually more difficult to verify. But in the natural group setting, we may ask that such a conditions might be enough to check proper actions or not. So in particular, so many examples shows that if the action is free, then the action is proper. And also many examples show that if all orbits are closed, then the quotient space is Hausdorff. But unfortunately, there are counter examples to the opposite directions. And here are the simplest examples that the things are not so easy. So let X be R2 removed by the origins. And we let act R by expanding and contractions so that the orbit is on hyperbolic curve. And this action is free. So there's no, the isotropy group is always one point. And every orbit, so this is the example of the orbit. And if we remove the origins, then the origin is not the accumulation point. So all orbits are closed. So this means that the quotient space is T1 topology. But actually, this action is not Hausdorff. For example, this point and this point cannot be separated by open sets. So actually, this is locally Hausdorff in the sense that each point as a local Hausdorff neighborhood. But as a global topology, this is not Hausdorff space. This is a quite delicate example. But it's not an artificial example, but it arises naturally in the SL2R. So namely, this space is identified with the homogeneous Z-mod N, where N is a nilpotent subgroup, and A is a diagonal groups. And A acts on Z-mod A and naturally. Then this actions is the same on this one. So this actions is that every orbit is closed. And of course, if we write in this way, then there's every isotropy subgroup is trivial because hyperbolic element simultaneously nilpotent element is automatically the identity element. So nevertheless, this action is not proper. Then by the duality, also one can see that the action of N on Z-mod A is not proper. And this is hyperboloid. So this is the Lorentzian manifold. And N acts on this space isometry. Because A is reductive group, so there's a natural pseudo-Riemannian structure, type 1,1. Okay, so this already in the case of SL2R, there are such a counterexamples. But if we consider more abelian-like groups, then still we may expect that proper actions is more or less a free actions. So this is Lipsman's conjectures. So Lipsman conjecture that if the group G is simply connected nilpotently group, in such a case, and if L and H are close connected subgroups, then he conjecture that the action of L on homogeneous space G mod H is free if and only if the action is proper. So in this case, the orbit is automatically closed. And this is true for two-step nilpotent groups, and also true for three-step nilpotent groups proved independently by Baklotti and Yoshino. But there's a counterexample for the four-step nilpotent groups, and the simplest example is five-dimensional manifold, nil manifold, acted by R2 abelian. In this case, L is abelian subgroups, acting on R5 in a unipotent way, and every orbit is closed, and the action is free, but the action is not Hausdorff, not proper, and the quotient space is not Hausdorff. So it's quite delicate. So the definition of proper action is very simple, but the property is quite delicate. So we want to give an, so now we have three directions. So one is that give an exactly necessary and sufficient conditions for proper action. And this is what we want to do today. And the second one is that not necessary and sufficient conditions, but we consider strengthen the properties. And tomorrow I discuss stronger proper actions. And this is better property that it is more likely to be stable under the small deformations of proper discontinuous actions. So I forget to say, but for proper actions, this is quite a fragile properties. If we have a proper discontinuous actions, and then perturb a little bit of these actions, then it may suddenly stop to be proper discontinuous. Tomorrow also I give very elementary examples that proper discontinuity is fragile property. But still, if we strengthen the conditions, and then we can chase some proper discontinuous action. So this is one of the topics. And the second one is that, so this is strengthen the definition of proper actions. The second one is relax the definition of proper actions like measurably proper actions. And this is connected with representation, unitary representations. So, but today we look at exactly necessary and sufficient conditions as a starting point. So for this, let us visualize some group actions, group multiplications. Suppose G is a group, not necessarily commutative. And H is some subgroup. Symbolically, I write this H here. And let's take S to be a compact subset. And then we multiply element of S here. So this HS is an element, is a subset of G consisting of the form AB. A is in H and B is in S. Then I symbolize this as a tubular neighborhood H. So it's not a difficult set. But then we multiply from the left because the group, we have an action from the right and left. Then if G is abelian, then still this SHS is kind of a tubular neighborhood H. So we can predict what the shape is. But if S is G is highly non-commutative, like SL2R, then this set might explode rapidly at infinities. So this shape will be responsible for the criterions of proper actions. Okay, so I shall use these definitions often. Okay, now the idea to give them properness criterions, we forget L and H are even subgroups. Just we treat L and S are subsets. And G is a group, locally compact groups. And then we introduce two binary relations. One is something like a transversality, and the other is something like equivalence. This transversality means that we have this SHS by expanding by compact set S. Then we consider intersections of this set with L. L is non-compact set. If L is kind of transversal set, then intersections will be small. So for example, its closures is still compact. And if we switch the role of the L and H, still we have such properties. We write L and H is kind of the transversal property. On the other hand, the second condition is that L is completely contained in this set if we take S appropriately large compact set and vice versa. In such a case, so namely L and H is more or less the same set up to multiplications of compact set from left and right. We write such symbols. So we have defined two symbols. What is the meaning? The meaning is the following. Okay, so maybe before that, I just give one trivial example. If G is Euclidean space, then and L and H are subspaces, then this conditions is nothing but the transversality, and this conditions is nothing but equality. And in general, if G is a locally compact group, and suppose that L and H are closed subgroups, then this definition is nothing but the action of L on Z mod H is proper. This is what we want to give a criterion. And by definition, we have a symmetric relations. So this means that L acts on Z mod H properly if and only if H acts properly on Z mod L. So we can switch the role of the H and L. And this conditions is actually equivalence relations. And this equivalence relations is just to save time in considering these criterions. Because if H and H prime is equivalence, then we have the same conditions. And actually, this equivalence relations is optimal equivalence relations in the following theorem. That this is a discontinuous duality theorem. That given a subset H, we collect all subset L in Z, which has these properties. And then these collections actually recovers H up to this one. So if we want to understand some persons called H, and if we know all his or her friends, and then we can recover from these collections to that person up to equivalence. So this is duality theorem. So it's a little bit similar to Pontelagin-Tanaka-Tatsuma duality that the unitary dual recovers G. Okay. Okay, so now we want to give a criterion for this one and also these relations. And we want a handy criterions, not just abstract equivalence, but we want to find some necessary and sufficient which are computable. And I explain its solutions in the case of real reductive groups. So suppose G is a real reductive groups, and we consider Cartan decompositions. K, and let W be the while group. And then we have a project from G to A by taking the middle part. This we call Cartan projections. And this is uniquely determined up to the conjugacy of the while group with respect to G and maximal split abelian subspace A. So A is not a Cartan, but maximal split abelian subspace. So the dimension might be smaller than Cartan's subalgebra. And in the case of the G equals GL and R, and this map is obtained as follows. We consider transpose G times G. This is a positive definite matrix. And then we consider the set of eigenvalues. All of them are positive. And then we take logarithm. And then this is a map mu G to this set. And this is well defined up to permutations, namely while group W, which is isomorphic to the permutation group of n elements. Okay. Then the properness criterions is given in the following formulas. This is what we want to know in the non-commutative setting. And this is exactly checked by knowing the Cartan projections of this set. And since this is abelian, we can easily compute this as far as we compute Cartan projections of this set. So this is properness criterions. And the first conditions is that the one directions is non-trivial. And this directions means if we consider perturbations a matrix, then of course eigenvalues changes accordingly. And then we want to estimate the error term of eigenvalues. And then we may ask that how different from the original eigenvalues. One is a uniform estimate, and the other is ratio depending on the maximal eigenvalues. And this gives better results, namely uniform estimate, not depending on the maximal eigenvalues. So this is an estimate of this one. And the second one is criterion proper actions. And then by using this, we also, so this is still qualitative result, but then we shall go to quantitative estimate of properness. And this uniform estimate of matrix perturbations of eigenvalues also will be used part of the proof of the some theorems in unity representations. Tempered homogeneous space. This one. Okay. So now let us give a quick proof of this one. But I just give a simplest case. And for simplest case, we consider a special case where H and L are reductives. So if, for example, G prime, either H or L, is reductive subgroups, then we can take compatible Cartan decompositions. And then we can take a maximal abelian subspace inside A after taking conjugations of G prime by some element of G. Then if H and L are reductive subgroups, then we can define AH and AL inside the subspace A. So this is the subspace of abelian group A. Then in the abelian space, A is Rn. This conditions is nothing but that this subspace has a trivial intersections up to while groups. So this is some subspace, and this is some subspace in A, which is easily computed. So this conditions is very easily computed. This is an criterion proper actions. In the set case, H and L are reductive subgroups. And in this case, this H, if we consider Cartan decompositions, then H and AH is equivalent up to some multiplications of compact subsets. So in our notation, this is equivalent. And this equivalent doesn't change the answers for proper actions. So the proof of theorem 5 reduced to the case when reductive subgroup is actually split abelian subgroups contained in A. So namely, we can consider reductive case just H and L are subspace of A, and L is exponential L or exponential H. Then what we want to prove is that this action is proper if and only if L and H has a trivial intersection up to while groups. And still, this criterion from right to left is non-trivial, and I give its idea quickly, the flavor of the proof. And the general case is a little bit more complicated, but there are some common idea inside. So this is a figure. So what we want to prove is that if this has a trivial intersection, the action is proper, or oppositely, if this is not proper, so namely, if L is something like here, and there's an infinite sequence inside going to infinity, then we have some non-trivial intersections of two subspaces. And for this, we write down these conditions that this is non-compact. And this red color is a convergent sequence. And this blue color is divergent element. And by normalizing it, this Tn is some real number going to infinity, and Yn is a unit element in the Lie algebra. And also Zn is a unit element in the Lie algebra. And then Tn goes to infinity, and this element, or Yn, Zn converges. And then by renormalizing or taking subsequence and also possibly replacing H by some while group elements, we may assume that this Tn and this Tn prime is actually equal. And the limit point lives in the same while dominant chamber. So this assumption is written in the following lines, that this is blue one is divergent sequence, and red one is convergent sequence. And the limit point lives in the both dominant while chambers. Then this is an assumptions. Then what we shall prove is that the limit point is the same element, which shows that this has a non-trivial intersection. And actually, that to do that, we consider we linearize these conditions, and then actually by using adjoint action, we linearize these conditions and look at each subspace. Then by some speculations of this projections to each root of weight space, we can conclude Y equals Z. So this is a sketch of the idea of the proof in the very simplest case. And so I give a couple of corollaries of this. So one is some criterions of the Calabi-Markus phenomenon that we explained for the de Sitter manifold is always non-compact. And for the pair of the real reductive groups, the following four conditions are equivalent. The first one is that Z mod H admits a discontinuous group which is isomorphic to Z, or Z mod H admits an infinite discontinuous group, or in our terminology, G and H is not equivalent. And this is equivalent to the real rank conditions. And the first two is clear. And the second is that if gamma is a discontinuous group, we have this. But if gamma is infinite group, then we have this condition. Then H and G must be not equivalent. And from this to this, it's just a Cartan decompositions. And then the non-trivial part, main part is that if this condition holds, then by using the our criterions, one can find proper discontinuous action by theorem. So this is an equivalence. And so this explains this example for general periodic groups and H. And so properly, so the previous examples for SL2R case, this is delicate examples, but the Cartan projections of A and the Cartan projections of the nilpotent group, both are the same. And so this is the same, so we have this non-properness criterions. So also this is an example. And lastly, I give one more examples that we consider SLNR mod SLMR, where N is SLM is embedded in this way. And then ask if there is a proper actions of SL2R on this space or not. Through some homomorphism phi from SL2R to SLNR. So for this, we just apply the criterions of this one. And suppose that the phi is an irreducible n-dimensional representation. Then the Cartan projections is looking at the weight of these representations. So Cartan projections of this SL2R is such a subset. And the whole Cartan space is Rn modulo R. So this is this space. And the Cartan projections of this SLM is like this. So we just look at the intersections of this subspace with this subspace. Then we give a necessary and sufficient condition. And this idea is generalized to the following theorem, that for any reductive symmetric space, the following three conditions are equivalent. It admits a surface group as a proper discontinuous group, if and only if it admits proper actions of SL2R, or it admits a discontinuous group gamma, which is isomorphic to Z, but not just Z, generated by a unipotent element. The equivalence of the first and the second conditions is by using the Yakubov-Morozov theorem. And then if SL2R acts properly discontinuously, then its subgroup, surface group acts properly discontinuously. But the converse statement also holds. If gamma, such a surface group acts properly discontinuously, then some SL2R acts properly discontinuously. And this is by using actually the whole classifications of such proper actions achieved by Okuda. So this is one application. So I think it's good to, so tomorrow I'll talk about some quantifying these conditions in two ways. So thank you very much for your attention.